Hi everyone. Today we'll discuss problem of the day. So this is our problem. It says that we have a coin of integer array. Uh, it's a array of integers and its size is n, and we need to create a sum using the denominations available in this array. Now denomination means that uh, what exact amount you can take from the coins array. For example, in India we have rupees 5 coin, rupees 2 coin, rupees 1 coin, rupees 10 coin, right? So but we don't have rupees 8 and rupees 9 coin, right? So for in India we have denomination only of these four types: 2, 1, 5 and 10, right? So by using these coins, one can say that generate this much amount. And one thing is also given here is that we have infinite supply of each type of coin. So given any set of denominations, you can take any denomination as many times you want, right? And then you have to create this sum. For example, one can say that uh, in my denomination array I have rupees 2 coin and rupees 5 coin, okay, and I want to create the sum equal to 10. Now one can say that just take 5 2 rupees coins. So you can take 5 2 rupees coins, their sum will be 10, right? Another way is just take 2 5 rupees coin, then their sum will be 10, will also be 10. So there can be different ways of choosing the coins and create our sum. Now we want to generalize it. We want to write a general technique or general formula to give me all the total number of ways by which I can uh, get the particular sum. Okay. So let's say you have an array where you have coin C1, coin C2, so on to you have, let's say, n number of coins. And let's say we start from the rightmost coin. Now for each coin, let's say I take any general coin, CI. So this CI coin, on this CI coin you have two choices, whether to include it or do not include it. So you can say that for any coin CI I have two choices: include and do not include. Right. Now when can I include this CI? Let's say I have a given sum equal to S. Now in what cases I can include CI? Now this CI should be at least should be at most equal to this S, right? It should be less than equal to given sum. If value of CI is beyond this sum, then we can't take this coin, right? We can't break a coin. Otherwise if we take a coin whose value is greater than sum, then it will exceed the amount, and we won't be able to make the sum S by using that coin. So for including, there's a condition that CI must be less than equal to S. Then only I can include it, right? Otherwise I can't include it. If this condition is not true, if Ci is not less than is equal to S, then I have no choices. I have to exclude the coin always if this condition occurs. Okay, so let us write this logic. I'm saying that if my coin Ci, its value is less than equal to given sum, then I have two choices: include it or do not include it. Okay, now let's say by including it, I'm getting number of ways equal to w1. If I include this coin in my set of coins, then I'm getting number of ways equal to w1, and by not including it, I'm getting number of ways equal to w2. So I'll recursively calculate that, right? Now what will I return? I will return total ways. Total ways will be w1 plus w2, right? Now how can we calculate the w1 w2? That will be see later. But let's say by including this ci, I'm getting total number of ways w1, and by not including this ci, I'm getting total number of ways equal to w2. Now what will be the final answer? w1 plus w2. If this is not true, if this condition is not true, then we have only one option, that we exclude this coin. So if we exclude this coin, exclude ci, and let's say I'm getting number of ways w3, and I have to return w3 only. Okay, now I can write a recursive code. Basically I have to iterate in all coins from C0 to Cn, and on each coin I have to make a choice whether I include it or do not include it. But before making a choice, I have to check if I can include it or not. If I can include it, then I will first include it and don't include it. If I can't include it, then I have no choice, I should exclude it. By that I will keep on calculating number of ways by recursively and return the answer. So how will the recursive code look like? It will be something like this. In my recursion function, let's say I'm calling this function as aux, and it will return me the number of ways. So I'm setting a type to int, and I have array of coins, right? That is also of integer type, and I have size of this coins array, and I have the sum that I need to make out of these coins. Okay, so in recursion, I will write the first case. If let's start with the rightmost coin, and I have coins n minus 1. If this coin is less than equal to sum, then I will recursively call for rest of the array, and let's say I'm getting a number of ways equal to w1. And how will I call recursive call? Aux. I will pass this array coins, now if let's say first of all, let's say we include it. I'm including it. So now if I include a coin once, I can include the coin again also, right? So I'm not increasing n to n minus 1. I'm just decreasing the sum by the amount of value which I have taken from the coin. Coins okay. So since I have taken the coins n minus 1 from this coin, this value I have taken from this coin, so I have to decrease the sum by this amount. And since I have chosen this coins n minus 1, so I can again choose it in future. That's why I'm not decreasing n to n minus 1. I'm keeping the n so that this coin can be chosen further. Okay, now next case, if I don't include it, let's say I'm getting number of ways from recursive call equal to args of, I'll pass array coins, right? Now since I'm not including it now, I will never include it later also. So I'll decrease my size of denomination by -1, so that this coin will not be taken further in future, and sum will remain same because I haven't chosen it. I hope you got why I haven't decreased n here by 1 and why I have decreased by 1 n by 1 here. If you're still not getting it, you can ask in comment, right? Now this is the case when I can take this denomination. Now what will be my answer? Answer will be return w1 plus w2. Cool. Now what if this condition fails? Then our code will not enter in this if block and we will reach this section below the if condition. Here I have no choice. I must exclude this coin because I can't choose this coin because its value is going beyond sum. So I'll just return args of coins n minus 1, and since I haven't chosen it, sum will remain same. So I have to return this value. So this is my recursion relation, or you can say recursive code for this problem. Now this recursion code will take huge time to execute, and my expected complexity is big of n times sum. So obviously we will apply dp here. And in dp you have two ways. Either you can use the tabular approach, or you can memorize it, right? So let's say let me use the tabular approach. In tabular approach, we create whether it is tabular memory, we create a vector according to our solution space. Now since our solution in our recursion function, the only two variables are this n and this sum. This coin is not varying. This is constant in every recursion call. But this n and sum, they are varying in every single call. So I'll make a array of, or in C++ you can say I will make a let's say I'll make an array of dp or t, you can say. Its size will be n plus 1 and sum plus 1. Okay, and I have to fill this array with sub problems answer, and eventually t of n sum will return me the answer, right? So first of all we will we have forgot the base case here, because we have to terminate the recursion at one point of time, right? So in base case I can say that if sum is equal to 0. Now if sum is 0, and you can have any number of coin, by how many ways I can create a zero value sum from the given number of denominations? That is only one way, that I don't choose any coin. So not choosing any coin is also a way, and that way is one way. So we will return 1. If I am not choosing anything, if I am not choosing any coin, that is also a way, right? And that is only one way, so I am returning 1 here. But if sum is not equal to 0, we will this condition will evaluate to false, and we will reach here below this if. Now I will check if n equal to 0. This means that I have run out of all denominations. I have no coins. Now if someone says that create this non-zero sum value with the coins that you don't have any coin. You don't have any coin, but you want to create this sum non-zero sum. There are no ways of doing it. We can't create a sum without any coin available. So there is zero number of ways of doing it. There is no way of doing it. So return 0. Now in tabular approach, we start with base case. We first fill the answer of base case in my DP array, you can say. So start from I equal to 1 to n plus 1. Okay. Now here I refers to my variable n, and j refer to a variable sum plus 1. Okay. So for I n plus 1 to from j 1 to sum plus 1. Okay. Here if I see that now in the base condition, this n this sum will be replaced by j. This sum will be replaced by j because variable j is taking account of sum, and variable I is taking account of I. So n can be replaced by I. So I can say here replace sum with j and n with I. So first of all we will create the base case, and one thing I forgot here, I should start my iteration from the 0th index. Since it's not 1 base index, it is 0 base index in C++ or in Java too. So if sum equals to 0, that is if j equals to 0, if j is equal to 0, then my answer is tj, it is 1. Else if sum is not equal to 0 but n is equal to 0, that means I equal to 0, then my answer is 0, right? That's what we returned here. So this is how we can create the base case. Now we have to further go for upper cases, higher value cases, because this is the base case was the smallest problem that we solve in recursion. Now we have to move to further bigger problems. Now I again iterate. Now this time, since I have already created the base case answer, so I have to start my range from I equal to 1 to n plus 1 and j from 1 to sum plus 1. Okay. Now again we will just see the recursion, how the recursion is going on, and by seeing the recursion I can convert it into the DP version. So what we did in recursion, we checked if this coins n minus, so replace this n with I and this sum with j. So what I'll do, I'll just replace n with I and sum with j. This condition is true, then answer of Tij will be what? Replace I here with n with I, sum with j. So what you'll get? Answer of Ti j minus coins of I minus 1. Ti j minus coins of I minus 1, plus we will have a number of ways. When I don't include it, then n will be minus 1, so I minus 1, and sum will remain same, so it will remain j as it is. If this condition true, then I'll do this, else my answer will be Ti of Tj, T of I minus 1 j. So once you write the recursive code, it's very easy to tabularize it or memorize it, and eventually once these iterations get over, you can return T of n sum as an answer. This will be my answer, right? You can get the PDF notes or the code in the description section.